So it's my pleasure to introduce the panel on fault-tolerant future. Our rock stars beside me, Dr. Travis Scholten from IBM, Dr. Dustin Moody from NIST, Dr. Carl Williams from CJW Quantum Consulting, Dr. Jay Gambetta from IBM, and staying with us, thank you, Dr. Troyer. I will let you kick off, and thank you all.
All right, thank you very much. So to help set the context for the panel in our discussion today, we want to recall a little bit of history about how all of us ended up on this stage. You know, those of us on the stage, and I think there's a few of you in the audience, worked on a paper that we put out in January of 2024 called Assessing the Benefits and Risks of Quantum Computers. We took a holistic view at the research literature around advances in quantum algorithms and applications, quantum applications in cybersecurity and cryptanalysis, and also the development around post-quantum cryptography standards, and tried to get a handle on the timelines against which we might expect economically impactful quantum computing, but also cryptographically relevant quantum computing. And since we published that paper in January of last year, it's been cited over, I think it was just over 50 times when I last checked Google Scholar. And we were really trying to help policymakers get a handle on the implications of this technology for the foreseeable future. Now, of course, the dangerous thing about making predictions is you might be wrong. And so the impetus for this panel was for us to come back, to revisit the conclusions in light of recent advances in industry, error correction, algorithms, cryptanalysis, et cetera, you know, and really take a look at what we concluded and share some of those thoughts with you today. So we're going to do a little bit of a lightning round, so very brief answers. All right. Question number one, what is your 50% prediction for the year in which we will see economically impactful quantum computing? Just run right down the row.
I will defer to my colleagues because this is totally not my area.
Of course.
I think the first impact will occur in the late this decade, but I would say at a 50%, a lot of things going on, 2032.
2032, all right.
I will agree with Carl. I think late this decade, 29, we intend to have the first fault-tolerant quantum computer out, and then early in the next decade, I want to scale it to a large enough size.
Yeah, I think we will have the first academic impact 28, 29. Then for utility scale, the has a goal of 33. I think that's feasible.
Okay.
Can be faster.
Roughly circa the end of the decade into the early 2030s. Okay. Same question, but now for cryptographically relevant quantum computing.
This side or?
Yeah, let's go right down the
All
list.
right.
I will find a question for you to answer, Dustin.
No, that's fine. Yeah, they have more expertise on this as well. I would throw out, it doesn't appear as imminent as we were once worried. It's still coming soon, and because of the risks, 10 years seems a very reasonable estimate for us.
Okay.
Look, there may be algorithmic or other breakthroughs that would change this. I think if you are a high-risk entity, I think you should have everything in place by 2032. I think for the typical person, 2034, 2035.
Yeah, we were just talking about it. So there are algorithm approaches all the time. For the machines that we're planning, I would put it at 2034. But data matters. And so if you're not already making your transition to a quantum safe now, I think you're already starting to be too late.
So I think it could be earlier because we said kind of the Nakamis replication with the upper timeline might happen in 2033 or before, and Shor's algorithm will run on a similar machine. So we have to be prepared that it might be earlier, but it could slip.
So sometime in the mid-2030s then. All right. And the last question, and since we talked about quantum safe, when it comes to getting quantum safe, are you in the post-quantum cryptography or quantum key distribution camp?
This one I can easily answer.
I was going to say.
PQC.
PQC, yeah.
PQC.
We're committed to PQC. So I don't see that there is a future with QKD, but I'm happy to be wrong, but we're focused on PQC.
We need PQC first, and then if somebody wants QKD as an extra layer of defense, it can come afterwards, but PQC has to come first and fast.
So everybody needs to be working on getting that post-quantum cryptography deployed across your organizations.
And again, for high-value networks, I will agree with Matthias. There may be a value in putting QKD as an additional layer specifically on high-value networks.
Yeah. But on top of PQC, PQC
Yes.
has to come first.
Okay. All right, let's dive into a few questions. So we're going to first think about the quantum timeline. Right, so our paper concluded that quantum's economic potential will arrive before cryptographic impact. But over the past few years, we've witnessed lots of industry advancements and updates to roadmaps and breakthroughs in quantum error correction, the realization of logical qubits, and et cetera. So how have those developments changed your core confidence in that conclusion? And what do all these developments mean for C-suite leaders, policymakers, who are trying to think about getting a handle on the implications of the quantum industry over the next 5 years? And we'll just sort of open up the floor for whomever wants to take this to start, and we'll let the conversation flow from there.
So I think there have been a number of advances. I mean, as the hardware has advanced, we knew that approximate algorithmic approaches would come along. The most recent one is this decoded quantum interferometry, so that some new ways that one might do some things. This helps both on the quantum chemistry, but it could potentially also impact Shor as well. And so I think both the advances in algorithms, which is occurring now quite rapidly, I would say, compared to just even 5 years ago. But 5 years ago, it really started picking up. And then the advances in error correction and mid-circuit error correction and other approaches has brought down the resources. So the resources it's going to take are dropping. And part of this depends upon the architecture of the computer. So, it may be that, one modality gets to Shor or to quantum chemistry before another modality. But I think that it's advancing. It's probably advanced at least a couple years since we wrote our paper, I would say.
Okay, but
maybe I could add. So you asked the first question about when do I see economic value. And at the moment, we define economic value based on when we can do these algorithms where we can prove are in the class that has an exponential speed up over classical computing. I would take the lens earlier and I'd put it back on the many people in the audience, many people in the community that are doing work. I do think the machines that we're building now are getting to a size that they cannot be simulated by classical computers. So the numerical methods, the heuristic algorithms, we shouldn't underestimate them. So I do think we'll see some scientific, rigorous demonstrations of quantum advantage this year, if we haven't already seen them by a few of the community that are working hard, as we go into the next year. And if we can boot and get more work behind heuristic algorithms, we could bring this in earlier. But that depends on algorithm discovery.
Could you clarify for the audience what you mean by a heuristic algorithm in that sense?
And now, in the classical space, there are many examples of algorithms that are very hard to formally prove, and they were either discovered with numerical methods. We are seeing more and more quantum versions of numerical methods emerging, some of them using classical supercomputers mixed with quantum computers. And I'm actually excited that if we give the direction towards the community that are doing this work, we could pull in some of those timelines. But your first question asked when I can be sure.
Sure. Yeah.
Algorithm discovery is just as hard as building a quantum computer.
So in the last decade, we've seen big improvements in algorithms. When I looked in 2014, a chemistry problem probably would have taken 100 billion years. Now it's down to hours.
Right.
So, and same, there were recently the advances on Shor's algorithm that brought the runtimes down, the near qubit counts down. The same tricks we could show can be used to bring the chemistry down, so that we still think you can do chemistry replications provably on the machines that are smaller or the same size as the Shor machine, so it comes earlier, and might come even earlier when we combine it need, as Chase said with the heuristic algorithms, with AI training and so on. I think that can come earlier. So it's time now to accelerate applications development.
Right. Go ahead, Carl.
To accelerate use here.
So one of the things I think should happen, and then again, I don't speak for any of the companies up here, but of course we have companies up here
You speak
building
for yours,
computers,
right.
and we also have companies up here who really care about security, and in fact, they're the same companies.
Yeah.
And so whether you're a Google or an IBM or a Microsoft, one of the things I think they should do is create the quantum doomsday clock. They can begin showing what you can break very small primes today, complex composite numbers today. And if you project out, you should be able to project out and kind of resource out when this is going to happen. This is basically a white hat kind of a thing to let the community know, look, this is coming. Because that is the best projection of when the real risk is. I think it is a service for, as our paper pointed out, our paper basically said, if you are going to advocate for building this hardware, you also have to advocate for PQC. And so they go hand in hand. If you're going to be responsible, you should do that. And I think...
Sure. Ever since NIST put out the challenge in 2016, we've been actively developing PQC algorithms. IBM has a long history in the security. So as much as we do in building quantum computers, we're building quantum safe. As I said before, I feel confident in our hardware roadmap. You can all see the public roadmap. I've updated it when I put fault tolerance on it. I still feel that this is going to be more of a step function. We're going to build out a system, and Shor's algorithm is going to require a machine of a few thousand qubits and in a few billion or more operations. And I don't think we're going to see that faster than 2034. So if you ask me for my clock, it's just a step function by that date.
Okay.
Yes, so we've been working on the PQC algorithms for a decade and longer, since the NIST standards out. We're starting to deploy them. We have the algorithms in the near Windows crypto library. What's important now is, as was said, is that as we build the machines, we have to make the NIGA world safe. That means globally, because the NIGA supply chain is global. We need to accelerate the transition globally. We need standards that's NIGA harmonized across the planet. And we need the NIGA NIGA security priority, not just for us companies, but for everyone.
I would add a bit as well. So yes, lots of the science of these algorithms are pretty solid. Dustin can add more on that. But the part that is the hardest is what's going to be upgraded downstream, and that comes to your supply chain point. And the second is the IT transformation is a very difficult task. So this is more a social problem or a business problem than actually a scientific problem. We've got to keep improving the algorithms, make them better and better, but we've got to keep integrating into the software. But the IT transition that we have to go through is going to take many years.
I guess since we're here talking about getting quantum safe and whatnot, let's just dwell on that for a little bit and say, maybe from your perspective, Dustin, right? Like, how should we be working together as industry, company, government, academia, right, to mitigate the quantum cybersecurity risk? I know NIST has the standards, right? But as Jay said, this is like a socio-cultural problem where maybe everyone's like, well, it's not such a big deal for me right now, and maybe I'll get around to it. And the urgent always takes priority over the important, right? And this is extremely important. So I'd appreciate your perspective on this about how we can foster more collaboration to get the world quantum safe.
Yeah, I think it's absolutely essential that we have cooperation from government, industry, other organizations, other standards organizations. From the beginning, when we began our standards process, we saw a lot of that cooperation. The submissions were from companies, academics around the world. They also evaluated them. We did at NIST. now that we have the standards, we're starting to see them adopted internationally. Other standards organizations like ISO or the IETF, they're putting these algorithms in these standards. And there already is a lot of cooperation, which is absolutely essential. If people are doing different things, our data and information is not going to end up being protected. Another good example of this is NIST is running what's called the Migration to PQC project through its National Cybersecurity of Excellence. And that's a coalition of, I think it's over 50 different industry partners and government agencies that are cooperating and working together to try and make the transition as successful as possible. Because like Jay said, it's going to be an extremely difficult, painful process. And we want to share the lessons learned. Everything is so interconnected. Every piece of software you have, your vendors, you all need to be transitioning together and talking together to make that work. So cooperation is absolutely essential.
Maybe could you make more concrete for that? Like you say, it's extremely difficult. I mean, it sounds like a really difficult thing, but are there a couple of very specific, concrete, tangible examples of that difficulty that people can really hold on to? Yeah,
a couple examples. So first, when I think of that, is the size of the PQC algorithms. They're a little bit bigger than what we're used to. RSA and elliptic curve were quite small, a couple hundred bits, but some of these algorithms are a couple thousand bytes that we have to put into. For some applications, that's no problem. They'll be able to handle that. For other protocols, that's bigger than what they're used to, so there's going to have to be significant changes to handle that. A second one, what was I just thinking of? Spacing it off the top of my head.
That's okay. Should we, Carl, do you want to?
Well, I just
while you're thinking, Dustin, right? Yeah.
You know, I'm sure my computer, my browser will get upgraded appropriately and everything else. Of course, I may have an old wireless router who needs a few upgrades. Yeah. And then there's the worst nightmare from my perspective is the biggest vulnerability is all the Internet of Things, because some of those, how many IoT things do you have in your house? I don't even know how many IoT things I have in my house. So I don't even know what needs to be upgraded and really what needs to happen with that IoT device. I need to throw it away and go buy a new one.
I mean, is that actually what you think is going to happen in that sense, right? That the only way to do an upgrade, in versus like a firmware update or something like that?
I think for some of those IoT devices, they become the ultimate risk factor left behind because they aren't upgraded, and as a result, this will be
not upgraded or not upgradable.
The weakest link. I don't think they're updatable.
Okay,
I think
but I'm just curious.
Link.
Yeah. Okay. Interesting. Jay or Matthias, you have anything you want to add?
I think we touched on most of it. I think what Dustin was saying, I agree these algorithms are a little bit more. It'd be interesting if we can see if even future algorithms can be less. So I don't think we should think of the algorithms as done. That's still important to keep investigating more crypto algorithms. But I think the way we always describe it is it's a culture change from crypto being sort of immersed everywhere to becoming crypto agile in the future, so that it's extremely easy to upgrade your crypto. We're going to have to move from a world where crypto was kind of diffused everywhere to a way where it becomes easier. If that means we need to put proxies or other things in front of some data that can't, sources that can't be upgraded, that's one answer. Or we need to understand where we can operate. But I think this whole culture, business, society, IT transformation that we're going to have to go through. And yeah, if we are very confident that these machines will exist in the 2034, 35 timeline, I don't think 10 years is too far away for not starting right now.
Yeah, I fully agree, and thanks to NIST, we know what we should do, and we know how we can upgrade Windows for that, but then the adoption is the problem. It's there's mentioned the social problem of how many machines out there that may still run Windows XP things, and so we need to get to a culture where security comes first, where people upgrade regularly, and the long tail will remain with IoT and with old machines.
So none of us can see the people out there, but raise your hand if you do cryptocurrency or blockchain, because I'll just throw this back. I mean, what of those are now PQC reliable? I think none of them, as far as I know.
Yeah, most of them all rely on classical signatures for authentication, all of which are vulnerable. So yeah, they will have to transition as well, which I'm not aware of any that have successfully done that all the way yet. Yeah, so.
So go crypto.
Go.
Yeah.
Yes, yes. That's a whole nother thread that we could get into about quantum and cryptocurrency and Bitcoin and Ethereum and et cetera. All right, so we spent a lot of time talking about the security risk and the need to get quantum safe. Let's look a little bit more on the economic impact side, right? So as we kind of enter this early fault-tolerant era, what are the most exciting developments in use case exploration that you see from working with your customers, clients, et cetera? And then if we think about businesses and governments that want to engage in a quantum journey and explore the applications in their business, what would you recommend as far as team building, developing pilot projects, et cetera?
Look, I think it's extraordinarily exciting, and you can see what different companies up here have done. I mean, you got Cleveland Clinic with IBM. Look, I think if it's not just the quantum computing. If you look at the quantum sensing things, this is going to really transition things. It's going to make life better. It's going to allow us to do new material designs, do other things. I think on the materials, whether it's chemistry or pharmaceuticals or lighter materials for things where you care about lightweight or better batteries or whatever, I think all this is going to come. So I think I think it's a beautiful future and exciting future. I wish I was just going to be around to see what it looks like in 40 years.
Okay.
So maybe what we often say is, I think everyone's seen us be transparent on our roadmap. The roadmap is so that you can, one, hold us accountable, but number two, you know what is coming. You know what we're building towards. And my view is that there's got to be, I want to call it scientific exploration now, where we're either coming up with better ways of handling errors, and there's many different companies that are doing amazing work with error mitigation techniques. And there are other examples where I think we're going to see rigorous scientific quantum advantage claims come out by our partners over the next year or so. I think that is all healthy. We have to get that to go. And so what we often say to our clients is, don't wait around. You should have a small team understanding this technology, understanding how it's going to impact your business, understanding whether it's going to have a big effect to your business model. And you don't want to be kept like caught off guard. We don't recommend getting large teams in the enterprise world to do it, because we're still in this algorithm discovery period. And as we go forward, as the more algorithms happen and as more synergies get found between AI and quantum, I expect that to only accelerate. And as fault-tolerant quantum computers at a scale of hundreds of logical qubits enter into the equation, I think this is only going to see more and more growth as we go forward.
Okay, cool. I think Matthias.
Yeah, I fully agree. That we've just seen the first logical qubits this last year. With the ion traps with atoms. We recently announced the sale of a commercial 50 logical qubit machine to Denmark. This is early, but it's the time now to start, as Jay said, to build teams, to think of the impact. Since scaling from 50 to 1,000, that will come faster than some people think. And so it's the time now to start exploring the use cases, the applications. We know chemistry will be one. It will change pharma, manufacturing, and more. That's a huge impact on the world. But it's the time now to start and explore that. And as it's early yet, as the commercial value is still a few years out, it's the time now for public-private partnerships, for making the latest machines available to researchers, to startups, to companies, so that those teams that Jay mentioned can start actually find out how it will impact their business.
So let me just mention one caveat, and the experts up here can correct me if they're wrong. You know, there's this big idea that we're going to solve all the optimization problems. And it seems to me that the only optimizations that we're going to solve are those that can be mapped to very small input, because the I/O problem, the input problem from a classical database is just a killer. And so I want to put that caveat out. It has to be mappable to a small data input problem.
Yeah.
So I don't think we should restrict as much as that. So first I'll say, the one thing where maybe I'll disagree with Matthias is, for me, logical qubits require having a quantum computer of order 100 qubits or more. Otherwise, you're just doing quantum device experiments, and no one is there yet. So I strongly disagree that we're in the logical stage. That's going to take, to get to 100 logical qubits working with, say, 10 to 100 million operations, it's going to take a few years. To go to your question, you can think of it as putting the data in and input, or you can encoding into, say, the standard Oracle approaches, and you get that. I think we should embrace creativity, and as we think forward, quantum circuits can encode information in the gates. And I'm seeing more and more results coming from our partners, not from IBM, where they're showing interesting results in novel ways of getting the data into the quantum computer by doing these operations. I would push back and say, let's let them explore these numerical algorithms. Let's let them make it rigorous before we get. I agree that formally, if you map optimization to a Grover's problem, you get a polynomial speed up. But I'm optimistic that the creativity in the optimization space can go beyond different ways that we've done it before.
Nice. So as we come to the time at the end of the panel, I'm going to ask you kind of a curveball question, which is, you know, all of you have had very long and illustrious careers in quantum. And I want you to think back to when you got started. And knowing everything that you know now, kind of what would you do differently? What's been most surprising? What excites you about this future fault-tolerant quantum era?
You want to start?
I would have moved earlier to company and started building machines.
Okay.
Yeah, so I got into quantum computing because I did my PhD on interpretations of quantum mechanics and convinced myself, rather than arguing over definitions, the only thing would be to build it. And that's what I've dedicated to. I think we could have gone earlier to go much more, as Matthias said, I went early into the industry, but for a long time we were very isolated silos. Yeah. What I see now is I see much more collaboration across public, private universities. I think it took a while for the community to understand what it can do well and how it can collaborate. And I don't know whether I could have made a difference, but I think if that could have happened earlier, I think it would have been better for everyone.
Nice.
So I agree with the comments that both been said. I was at NIST when we started our quantum program in the year 2000, and we started the program not because we thought we were going to actually do something useful, but because we were gotten to a point where we wanted to know where, can you really build a quantum useful device? Mm-hmm. And again, we've been building clocks forever, but I mean, this was more around the computing side and the communications side, and we went out and did single photon detectors. I have watched this transition, and I think it would have been great if there had been a little more industry engagement. And there were always companies in the field, but again, even Microsoft was first software and a little on the hardware side. Everybody kind of stepped in a little more gradually. Google did everything else. I think it should have had.
IBM was there from the start.
IBM was there from the beginning.
OG IBM, quantum company.
IBM was there from the start, but I think if it had started a little earlier, we'd be a little farther along the line. I agree.
Yeah. So starting with all of them, starting earlier, PQC, it would have been great if we could have been a little bit earlier as well. I mean, we're proud that we have the standards here, and we feel that we will be able to transition in time. But having a few more years would certainly be a good thing to protect our information into the future, because you need to have it all protected well in advance of when a quantum computer is out there. So,
nice. All right. Well, thank you all for your comments and your participation and your insights. Please thank me in joining the panelists today.